Hello, everyone, and welcome to our third webinar, Building a Recommendation System in AgensGraph. It's really nice to have you all here, and again, thank you for joining us. Today, we are going to learn how to power more accurate recommendation system in real time by using AgensGraph. My name is Aya, and I'm a technical engineer with AgensGraph team. I'm responsible for AgensGraph consultation and support of the AgensGraph. As we all know, real-time recommendation engines are an important element when it comes to the success of the business, especially online businesses. Making relevant recommendation in real time requires the ability to correlate product, customer, inventory, logistics, and also the suppliers. So by saying that, one of the essential technologies for having a real-time recommendation is a graph database. A technology easily databases, the other databases for connecting volumes of connected data to gain insight into customer needs and also the product trends. Here at Bitnine, we focus and develop a multi-model database to achieve all these goals. Our team in different locations and offices all around the world, such as Bay Area, Santa Clara, London, Tokyo, and Seoul, South Korea, are offering our outstanding performance and services such as graph consultation, graph algorithm, feature development, data analysis. Today's speaker is Joe Fagan, Director of Pre-Sale, who is responsible for shaping Bitnine's pre-sales and also technical marketing strategy for the region and helping customers create innovative solutions, implementing graph technology based on AgensGraph. So before I hand it over to Joe, I just wanted to quickly mention that you can send your question anytime through the chat box for this webinar, and that we will answer the questions at the end of the webinar. So again, thank you for joining, and now let's see how Joe is doing. Hi Joe, how are you doing today?
Hey, I'm doing really well. Yeah, the temperature over here is I'm in middle of England, and it's 35 degrees, so we're really enjoying the heat wave, and it's a great place to be, right in the middle of this heat. Yeah. So thank you everybody for coming today. I hope you have a pleasant next 45 minutes or hour maybe. So the subject today, as Ao has already said, is graph databases. And graph recommendation systems, I should say. So we'll have a brief introduction to recommendation systems. It will be very brief, and then we'll talk about a couple of main theories in recommendation system engineering, and I'll focus on one, which is collaborative-based filtering approach, because it's the easiest. Then we're going to look at some arithmetic just to see how things are calculated. And then we'll import some data into AgensGraph, which is very similar to what Aya did last week in webinar number 2. Then we'll create a graph, we'll create ratings and similarity edges, and then finally we will create the recommendations and suggest further enhancements to recommendation systems. So what is an RS? My attempt at a definition is a recommendation system finds for each user the product most likely to be relevant. And recommendation systems are used everywhere. The product or service could be a playlist from YouTube or Netflix. It could be content from Facebook or Twitter. It can be people from LinkedIn or Badoo, which was new to me. It's the largest dating agency in the world, Badoo. It's 500 million subscribers. And then, of course, there's products from every website you ever visit. The outcome for people who implement recommendation systems, even naive ones, is between 15 and 35% increase in sales and up to 80% increase in screen time. And it turns out that implementing a recommendation system returns the highest return on investment than any other investment in data analytics. So the first RS only arrived in 1994. Today, 35% of all purchases on Amazon and 75% of what we watch on Netflix, and I'm sure YouTube, comes from recommendation systems. It's not all positive outcomes. There are some negatives. One is polarization. There was an article last week in BBC News about the flat earth conspiracy. I hope I'm not offending anybody, that maybe there are flat earthists among us, but nearly all of them said that they first came to the idea through the video sharing platform YouTube. And they also interviewed the guy who wrote the original engine. And he explained that, of course, they weren't focusing on finding conspiracy theorists. What they actually found was people who would watch videos intensely. They would stay for longer. They would click more in the recommended group, so they stay in that pool of recommended videos. And subsequently, you know, as a consequence, there's more screen time and consequently more revenue opportunity through advertising. But unfortunately, the World Wide Web can become a bit of an echo chamber for us as we just go in there and hear our own views echoed back time and time again, rather than exploring different opportunities. So we have to be socially responsible when it comes to recommendation engines too. So on this analytics journey, the ultimate is to go from descriptive all the way to prescriptive analytics. Descriptive is what we've done for 30 years using Excel or something similar. And we just do graphs and do monthly sales figures and sums and averages and maybe see patterns. And we just describe the data. We say, okay, look at this. We happen to sell more hats in the winter. Wow. And then diagnostic analytics is a little bit more sophisticated. It implements functions in Excel like correlations and regression testing and things like that. So it can come up with correlations and reasoning, and it might deduce magically that because it's cold, it's the reason we're selling more hats, not specifically winter. And then predictive analytics starts to return some value to the business. Up to now, it kind of cost the business money to do this stuff. There was no immediate return on the investment of the business analytics people. Whereas now it's starting to turn some more money for us, because we can do predictive analysis and make sure we have the logistics and stock and price and everything else geared up for next winter when we'll need more hats. And then prescriptive analytics is actually writing the future. A perfect example would be to make it colder and consequently drive more hat sales, but making it colder is a challenge that faces us all in the era of global warming. So this is just an example. I don't suspect we can do it. So recommendation systems live somewhere between this predictive and prescriptive world. Predictive because it can predict that people will watch the videos that we offer them, especially certain types of individuals. And prescriptive is because we can literally dictate almost to them what videos they will watch. So this is where we are. And this is the return on investment. And recommendation systems are the easiest of the, let's say, linear algebra based data analytics. That is the kind of the first year for a data analytics student. So it's just past the end of a good Excel course and starting into the world of business of the proper data analytics. Fine. There are two basic principles that the world works to when it comes to basic recommendation engines. One is called collaborative filtering, on which we'll focus today, and the other, by contrast, is called content-based filtering. Collaborative filtering works on a simple principle that people who agreed in the past will agree in the future. So Alice here has bought the blue and the green book, and so has Bob. So they seem to be in agreement about blue and green, or rated, I should say. It doesn't really matter, bought, rated, whatever. Alice likes, put it that way, Alice likes blue and green, and Bob also likes blue and green. Now, Alice also likes yellow, which Bob hasn't experienced yet. So let's recommend yellow to Bob. And that's the fundamental principle. If we look at content-based filtering, it requires knowledge about the subjects of the book or the product. So that the product has to be parameterized. If it's music, it has to be by genre, by artist, by composer. Maybe by style of music, maybe it counts drum and bass beats, I don't know. But there's one music distribution site that parameterizes music on 400 different parameters. So if Bob buys this maybe book on sci-fi, then this is another similar book on sci-fi, and we should recommend that book to him. Now, it's worth noting that this system requires knowledge of the products. And this over here requires no knowledge of the products or even of the people. The only thing that it's known is that Alice is similar to Bob based purely on their preferences and ratings and purchases. So we don't parameterize Alice or Bob in any way. We don't track their age or their gender or anything else about them. So there's nothing here that is content-based. It's simply this whole collaboration principle. And over here, it's entirely content-based. Now, from a cold start perspective, this is more difficult. If Bob just joined the group and hasn't made any purchases yet, it's quite difficult to get him started. So that's called the cold start problem. So what you would recommend in the first instance is the products you want to flush through, or the most popular products that you have. Whereas over here, you can get started after a single purchase. You can already start to recommend products to Bob even after his first visit. Okay, so they're the two principles. Many engines, like the most sophisticated in the world is probably Amazon, use a combination of both, together with a whole plethora of other things like viewing time, browsing history, and a whole host of other features. Find the very starting point in any collaborative filtering method is a matrix that describes the ratings between customers and products. So we have products in rows and the customers are down the side here. So this 2 here means that customer 1 rated product 3 as number 2. Now notice I've given them anonymous names because I know nothing about them. I don't know their names, or I don't need to know their names. And similarly with the products, I don't know what categories they're in. I know nothing about the products. And I just simply have a rating matrix. It's called rating matrix in the theory, but it might not be actual ratings. I mean, it could be explicitly ratings, like the customer has specifically rated the product, or it could be implicit. So you don't have a rating system on your site, but you can watch purchases or frequency of purchases or recency of purchases and deduce from that information how a character likes a product, especially if it's a consumable like bread or milk or something else. Just simply counting the frequency of purchases will give them a good indication as to whether they continue to like it or not. And now with the recommendation engine, if we take, for instance, say this character C4, well, the products that he hasn't bought are P3, P8, and P9. So which of these 3 products should I recommend? In fact, I want to populate this entire matrix. I want to fill in all the blanks, and then I will be able to answer the question, which product should I now recommend to every single customer? So if C2 jumps on the site, I pick the largest of these blank values, and that will be the most recommended product. If I have a slot for 5, I'll recommend all 5. And I'll prioritize them based on how much I think, or we're going to calculate, the customer will like that product. So if we can just zoom in on one little block here, if we answer the question, how do we do it for one block, then we just rinse and repeat and do it for every other block. So the question is, how will C4 think about P3 if he's presented with that product? Will he find it interesting, engaging? Will he buy it? If he buys it, how will he rate it? Those kind of questions. And we've very little information about P3. All we know is that we have 3 other customers who purchased the product. We have C1 purchased it, C5 purchased it, and C7 purchased it. Now we could say, okay, well, this guy has a low rating and this is medium, this is pretty good, and this is really good rating. So what do? Do we just average these 3 numbers? That's not a very rich way of doing it, because it leaves out one thing. It leaves out the collaborative principle. The principle that says that people who are similar to C4, we value their opinions much more than other people. So we have to have this concept of similarity between customers. We want to find the people who are kind of in C4's group. If C4 happens to be Bob, we want to find all the Alices, the people who are similar to customer number 4. And this is a similarity matrix here that measures somehow the similarity between the customers. So C1 and C2 are very similar at 0.7. 1 is identical, 0 is completely different, by the way. And so, of course, this is replicated here. This is a mirror image of this because C1 to C2 is equivalent to C2 to C1. I just left it there for completeness. And of course, down the leading diagonal, we have 1 because C2 is identical to C2. So we don't need to calculate it there. So what I'm going to do now is just switch to show you how we calculate similarity. And the way we do it is we consider, say we want to compare C1 and C2. We consider this row of numbers here to be the coordinates of a point in a 10-dimensional space. Now that might be difficult to get your head around, but let's go to imagine 2 dimensions. Do you remember in the old coordinate geometry, Cartesian geometry, you could plot a point 3, 4, and you could plot the point 5, 0. Well, let's even stretch our minds to 3 dimensions. We could do 3, 4, 2 and 5, 0, 0. And this is what I've done on this page here. I've taken C1 and C2, and I've just taken the first 3 coordinates only because I can't draw in 10 dimensions on a 2-dimensional screen. So this is one vector here. This is the 3, 4, 2 vector. So I go over 3, over 3, across 4, and up 2, and I get to this point here. And the other vector is 5, 0, 0. So it's 5, 0 in the other 2 directions. So it's lying along one of the axes, the P1 axis. Now, if these 2 persons are pointing in the same direction, if they're the same customer, for instance, they're going to be pointing in the same direction. They'll be identical. And what we're really interested in is the angle between them. And if the angle is large, then they're different. They're just pointing in different directions in this multidimensional space. And if they're really similar, they'll be pointing in roughly the same direction. And if you remember from your arithmetic, from your trigonometry, the cosine of a small angle is 1, nearly 1. So cos of 0 is 1. And the cosine of an orthogonal angle, 90 degrees, say, in 2 dimensions, the cosine of that angle is 0. So we have exactly what we want. If we simply measure the cosine of this angle for free, we immediately get a similarity score between C1 and C2. In this scary equation here, A is C1, B is C2, and this is how we calculate the cosine. It's this scary thing over here, but be not scared. This term here is going to take all the components of A and square them. It sums from 1 to 3, it squares them, it adds them all together, and then it takes the square root. And you might recognize that as Pythagorean distance. So this is simply the length of that vector. It's that length. And this here is simply the length of the other vector. So these are really easy to figure out. You just literally square these, add them, and take the square root, and you get this value here. Up here, it's just as simple. What we do is we're going to multiply this 3 by the 5, add it to the 4 times the 0, add it to the, add them all together, and that gives us the numerator. So we take the numerator, which is the product, taken in pairs. So it's the sum of the products, really. And then we divide by the product of the lengths. And that gives us a similarity of 0.56. That's how simple it is to do cosine similarity. And it becomes a really rich way of comparing customers. So now we have the 3 customers who bought that product. And they are customer 1, customer 5, and customer 7. Now, I really want to favor customer 7's opinion, because C7 is in C1's or C4's group, let's say. He's the closest customer to C4 who has made the same product choice. So we're really going to favor this number here, the C7's contribution. So this is going to deliver 3. 5 times 0.6 is 3, whereas this one, the 0.2 for C5, because I'm multiplying by the similarity, I'm scaling down. I'm caring less about the fact that he likes this product. And similarly, if he disliked it, I'd be doing the same. And for C1, it's about middle of the road. So this brings along 1, this 0.8, and this brings along 3. And this is a little a scaling factor just to make sure I land in the right range between 0 and 5. And that's the crux of deciding how C4 might like P3. And the answer is, our estimate is, he would like it at 3.7, so somewhere between a 3 and a 4. And it's very much influenced by the fact that C7, who is very close to him, is a 5. So I hope that explains similarity and the fundamental principle behind filling out this rating matrix. And you know what? We're almost done. That's it. That's kind of it. So What I'm going to do, actually, maybe I'll tell you what I'll do. I'll flip over to Excel and we'll go through the mechanics of that in Excel, so that when we're going to switch to Cypher and have a look at it in Cypher later. So this is raw data. This is just raw data. It happens to be purchase history, but that doesn't matter. I'm going to make implicit ratings out of this simply by saying, okay, well, this customer, he bought 40 products in total. 4 of them were this product. So give it a point. I just divide one by the other and get 10% or 0.1. So these are my implicit ratings, and they happen to be normalized, so they all add up to 1. And I just do one more little massage on it, and that is, I want the favorite product to be 1 and the least favorite product to be 0 or not rated at all. So this is just this keeps my product rating between 0 and 1, which is really what I want. So then I run the cosine similarity, and remember we did C4 to, let's say we want to compare C4 to C1, yeah. So if we look at the arithmetic and the numerator, this is it here. I'm able to calculate that by only looking at this vector and this vector. This is C1's rating, C4's rating. And here's the arithmetic again. This here is the size of the C1, which happens to be that. It's called a norm or a length. This is C2, which happens to be that. And this here is the sum of the products. And Excel has a nice little function that will multiply this by this, add it to this by this, this by this, and add them all up together. So it becomes really easy to calculate cosine similarity in Excel. And there are my cosine similarities. And then for the recommendation, the question I was asking is, how am I going to, what recommendation will I make for C1? Okay, so I want to find out, remember what C4 thinks about, but let's ignore that for a second. For customer 1, what do we need to do? We want to find out how customer 1 rates all the products. So what I do is I take all of the people who rated product P1, multiply their similarity to the individual customers, and then average them in some way. So we'll just go through this in slow motion. I want to know how C1 is going to rate all of these products here. Now, some of them he's actually rated, but hasn't rated the 2-star products at all. So let's take this one for an example. How am I going to fill out this value? Well, I'm going to look at C1 similarity to C4 and multiply that by how C4 thought about P5. So multiply C1 by C4 similarity, and then multiply that by C4's opinion of P5. I hope this isn't too complicated, but let's see where we're going. So I'm taking how C1 is similar to C4 and multiplying by C4's opinion on C5, and that allows me populate that little square. So now I have the opinions of all of the people who looked at that product multiplied by their similarity to C1. And then I do a weighted average of that, and it gives me this number here. So of the products that C1 has not purchased, this is by far the favorite product. This is the least favorite. Well, there's only 2. If I jump down to C4, for instance, C4 did not purchase this product, or this product, and this is the favorite product for C4. And that's it. That's how we do it. Now, for the we've used very little data. In fact, the entire data is 49 lines that look rather boringly like it's a table with three rows, columns: customer, bought, and product. I have my 8 customers down here. I have how many they bought of each product. I've got 49 lines in total. And what we'll do now is we'll jump over and have a look at some Cypher and see. This is a few lines of Cypher that's able to both create the graph, create the cosine similarity, and create the recommendation score for every customer and product. So before we jump into the code, because I don't want to frighten you if you're not familiar with Cypher, here's a very brief introduction into Cypher lingo. First thing is that it follows a kind of an ASCII art type of topology. You have a customer node here and a product node here, or vertex. Vertex and node are equivalent, they're the same thing. And then you have a relationship, which is in this case called buys. And And the base notation is this. If I want to refer to this relationship here, or any relationship, I have a roundy bracket, which means a vertex. I have a squaredy bracket, which means a relationship. I have a directional line there. And then finally, I have another vertex, which is, as always, in round brackets. So if you look at anything here, if it's in round brackets, if it's a node or a vertex, if it's in square, it's a relationship / edge. And this gives the direction. That's it. And then we have labels. We can have labels on all of them. We can label all the customer nodes with the label cost and all the product nodes with the label prod. And labels are preceded with a colon. So anytime you see a colon followed by a string, that's the name of a label. So this is the label of that node, and this is the label of that relationship. And then we can have short-term identifiers within a code block. So if I identify the customer I'm interested in, I can refer to that customer time and time again with the string XX, or I can refer to this relationship with the string OR and product Y. And finally, inside curly brackets, I can put as much data as I like in each of the nodes or the relationships. So for instance, in this example, inside curlies, I have a property name and a property value. So in summary, if you see a colon followed by a string, you're looking at a label. If you're seeing a string followed by a colon, you're looking at a property. If it's inside brackets, it's a value. If it doesn't have any strings or colons or it isn't inside a bracket, it's an identifier. So that's the lingo of Cypher, and it's becomes after a couple of hours of practice, you become quite proficient in Cypher. I'm kind of new to Cypher, and I managed to put this together. So first of all, this is where we start. We're just going to create a table that exists called purchases, and that's where I'm going to put my data, that column, 3 columns of data. So I'm going to create that. I will just pop it into, this is Postgres. Well, it's AgensGraph, so it's a heavily modified Postgres that happens to understand Cypher as well. So these are Cypher commands. And what I've done there is I've deleted the old graph just so that we can start from a fresh start. And I've created a table called purchases that has 3 columns, customer, quantity, and product. It's currently empty, but I've created the table here, and it confirms that it's told me that it's created the table. So the table is created now. We could actually look at its values if any of you are familiar with Excel, SQL, and you'll see that it's completely empty, but it has the 3 names, customer, quantity, and product. And then I'm going to take the data file that you saw, and I'm going to simply copy it row for row into the table. So I can do this, copy it in there. And that's as difficult as it is to import data. Sorry, that's as difficult as it is to import data for into Excel. That one's wrong, excuse me. Okay, and now if we run this statement, we will see that we have the data. C1 bought 4 of P1, C1 bought 7 of P2, and so forth. Right, so that's now in a table. And now how do we go from a table to a graph? Well, the first thing I'm going to do is I'm going to create a graph and give it a name. Command. I need to set my graph path so that when I refer to a graph, it'll refer to the correct graph. And then I'm going to create 3 labels called customer, product, and an edge vertex, or an edge relationship called buys. And then I'm going to load each row from the purchases table. There were 49 of them. I'm going to call each row by the name row. And here you can see that I'm going to make a node or a vertex because it has 2 curly brackets or round brackets. And this is where the properties go. I'm going to create a property called C and give it the value of cost column from the purchases row. So in other words, I'm going to look at the first row of that table that you saw, and that will result in me making a node called C1. I'll refer to it as X in here, but it's going to, this value is C1. So it's going to set a property called C as C1. So it'll do this. It'll create a label called cost with a property C and a value C1. And this will do almost the same. It'll go to the product row, product column in the row, which happened to say 4. and which happen to see P1, and it'll create a product node of label product, and it'll put P1 in that value. And finally, I want to merge those two together with the quantity, which is the middle column. So I merge my X to my Y, and I set the label as buys. So now I've created a buys edge, and I set the quantity to the row quantity. So that's its entirety, and we've now already created, with just those couple of lines, we've created our first graph and populated it. And now I can look at the data in two ways. This was in the table, which we saw earlier, and this will show me the data that's in the graph. So if we run that, you can see that we have the data C1 bought 4 of P1 and so on, and we have our 49 rows. So that's it. That's how difficult it is to create a graph based on data that you already have in a CSV file. Now I just want to create the ratings. To do that, remember, I had to get the sum of the I had to get the sum of products bought for each row, and then I'm going to divide the actual quantity and divide it by the total quantity and call that rating. So I'm create a new edge called ratings. Then I'm going to normalize that. So I'll do this all at one step, and then we will see I've created my ratings matrix. Okay, so if I run this code here, it'll create a ratings matrix, and it's updated a property at 49 properties. So it's created 49 rating edges between customer and product. So I have, in other words, I have that first matrix table that we started with when I showed you both Excel and the PowerPoint presentation. Now, the next thing I want to do is I want to calculate the cosine similarity. Remember, one of the things I needed was the norm or the length of each vector, and this just simply does that. It'll find every occurrence where a customer rates a product. Then I'm going to square each of the values. Then I'm going to add them all together, and then I'm going to take the square root. And I'm going to save in the node. I'm going to call it the length property in the node C. C refers to the customer. And that's where I'm going to store the lengths. So this will store the lengths or the norms of every vector that I need time and time again for the denominators of my when I create the similarity. And so the cosine similarity, remember the numerator was, I take this is the customer X, this is the customer Y. I'm going to take the normalized rating for X, the normalized rating for Y, multiply them together, add them up together. Then I have, this gives me the numerator. Then I calculate the denominator, do one by the other, and I've got the similarity there. So if I do all of this, I will create the similarity. Okay, so let's do all of this. And then I should have my similarity matrix. Okay. Right, and now I have 27 similarities. So I've inserted 27 edges. Now I'll just switch back here and show you something that may be of interest. Remember when we were back here, we saw that there was a lot of redundancy in this because this is duplicated. Very often these are very sparse matrices because not many customers, I mean, Amazon has something like 500 million products and a few, a similar number of customers or a bit more, but it's a really, really sparse matrix. And storing sparse matrices in graphs is completely natural. I don't have to specify this is a matrix. I don't have to specify its dimensions. I don't have to tell it how to handle blank empty space. There's absolutely no data redundancy. I'm not storing anything twice. A customer appears as a node in the graph in one place and one place only. And everything associated with that customer is either edged to another node or it's held as a property in the customer node. And if you add these up, you'll find there are 27 values here. C3 to C5 have no similarity at all. So there are 27 values there, and that is precisely the number of values I stored. So from an efficiency perspective, a space efficiency perspective, it's quite remarkable. I'll say it again, I didn't create a matrix. I didn't tell it what the dimensions were. I didn't tell it what the type of object that would be in the matrix. I didn't mention sparsity. And for free, I'm able to join all of the customers to all of the other customers with edges that store their similarity if they exist. Fine, so we have got the similarity now, and if we wanted to view this, if we wanted to have a look at that similarity, here I'm going to match every customer to every other customer where they have a similarity, and I'm just going to have a look at the customer name and call it customer X. I'm going to round the similarity to 2 decimal places and call it cossim, so that'll be the name of the column, and here I'm going to have a look at the Y's name, which will be maybe C2 or whatever, and then order it in this order. So this is how you create little, and of course I could export this to Excel or to a CSV file or do anything I choose with it. But let's just have a look at it in here first. Okay, so that's what it looks like. And by the way, I went into Agents Browser and had a look at this as well, which I can do. Agents Browser is a tool. I went into Agents Browser and I had a look at this as well. So these are the customers that we have here, and these are the edges which are the similarities. And remember, C5 to C3 did not have an edge. And then if I want, I can click on any edge and get data about that edge. So if I click on this edge here, it'll tell me that the similarity score between those two nodes is this number here, which is probably illegible on your screens. But that's Agents Browser. It's a good fun tool for exploring graphs. Fine, so let's jump back to the next piece of our Cypher. The next thing I want to do is I want to create the recommendation edge, which is just doing that arithmetic of multiplying how similar a customer is by how he rated the product, and then just do some normalization just to get the things in the 0 to 5 range, or 0 to 1 range in this case. So this will create all of the recommendation edges. So we do this here, and that updates properties. I updated them all, not just the ones that were empty, for the simple reason that I wanted to suggest for frequently bought products like consumables, I still have that data if I need to access it. It'll give me to re-recommend for a consumable product. And here now I can view the recommendation edges of the products that are not yet purchased. So I'm saying here, find me where a customer sets a recommendation for a product and he has not bought the product, where not exists this relationship. And then return, I'm going to have 3 columns: customer, the rounded recommendation, rounded to 2 digits, and the product, and order it in this way. So you can see that this Cypher language is really friendly, very easy to understand. And now, for instance, it's telling me that C1, we calculate, C1 thinks that P7 is a 0.49. This is scored between 0 and 1, so it's like middle of the road. And if we compare that with the results that we got from our Excel table, if I can find the correct Excel table. Yeah, I was there. So it's on the calculation sheet. So C1 rated P7 as a 0.49 and P5 as a 0.16. So let's see if we can compare the data here. And let's go to C3. What does C3 think? C3 favored product 4 at a 0.6 and product 6 then as a 0.51. So let's see, is that true? So he favored product 4 with 0.6. The asterisks indicate products that weren't bought. And of the ones that weren't bought, this was definitely the favored product. And the second favorite product was P6, which has a score of 0.51 or 0.506. So it seems that we have done exactly in Cypher as we had done in Excel. To my mind, it's actually easier to do it in Cypher. And now that we've done that, we can flip back, have a look at some of the outputs that we saw in Agents Browser. So this is what's called a meta graph. So this is now the completed graph. It looked at what we've done. We had 8 customers. It can size the nodes by the relative size number of objects of that label. So we had 8 customers, we had 10 products. We created 4 edges. a buys edge, which is directly from the data, a rates edge, which was normalized data, an implicit rating, not explicit. We created a cosine similarity that was between customer to customer, and we created a recommendation edge. This was similarity, I showed you that once before, and this is rates. Now, you might notice here that it kind of identifies the fact that there seems to be two little pools of products. P3, 4, 7, 9, and 10 seem to be one pool of products, and this is another pool of products. C3 bought these, and C4, 5 bought these. But it might be that these two products are product categories that you probably might not be aware of. So just visualizing data gives you the most unexpected insights that you simply could not pick up from looking at the data in a table or asking questions via SQL. I should say that SQL can do absolutely anything that Graph can do. It's just that Graph can do it so much more simply. So that's kind of where we've got to in 45 minutes. And finally, if I may, I'll just make a few recommendations, a few things that I would change if I were to do it again from scratch. The first thing is I would have used cosine centrality in the ratings, and I'll show you why. If I may, I'll just go back here. One of the issues, one of the heartburns, I don't like this system because if a customer does not rate a product, we're giving it a 0, and 0 is a bit harsh because that's indistinguishable from the customer really disliked the product. So what I'd much rather do is drag this so that the ratings for P5 and P7 say are the average of what C1 rated his products. That's a smart way of doing it, and this almost does the same. What I actually do is I take the average of the old ratings and subtract every number from that average. So it turns out now that we're 0 centered. A product rating of 0, which is P5, means I'm indifferent about it, not I dislike it or like it. Especially it's not I dislike it. So this is centered around 0 now, and it's much richer because now I can see that P8 really likes that product and actually quite dislikes this product here. So it also avoids, it smooths out harsh and easy raters because you're subtracting the averages. Another thing I would, I'd calculate similarity by category, because what I would do is if I had say 3 categories in my e-commerce site, I'd literally divide it into 3 categories and do a recommendation system engine in each category, which give me much more accuracy. If you have enough data, you can do categories as you have, but you need a decent amount of data in every category for it to be valuable. For consumables, I'd show products already purchased, not just the ones not yet purchased. And for books and music, I'd show similar products. It's an interesting point, but if I could have turned that matrix on its side and put P's down the left and C's across the top, and of course the customer or the product doesn't know I've done that, I could run exactly the same routine again, and I would bizarrely be able to find products that are similar just using cosine similarity. Although I know nothing about the products, I could still find products that are similar in that data set. So so you can actually do a form of content-based filtering, although you know nothing about the content. Okay, the other thing I would do is factor in business preferences for vendors, products, and categories, maybe based on margin, stock returns, strategic direction, whatever. So for each product, for instance, I would have a handful of factors like how much stock we have, what margin do we make, and what's the returns rate like on the product. This is stuff that might not be visible to the customer and certainly not visible to the recommendation engine. And then I would say, okay, what are my scaling factors? How important are these factors to my business? And these would be the business decision scaling factors. Then I'd multiply these two together, sum them. Now this is the old recommendation that I have, and now I'm going to scale it by this factor here to produce a final recommendation. When I've done this with all my recommendations, say I have 100 recommendations, but I can only display 10 to a particular customer. Which 10 do I pick? This will decide which 10 I pick. So as an example, say F1 is stock, F2 happens to be margin, and the business objective says, look, we need to reduce our stock holding is way too high. Let's start reducing stock. Then the priority would be to increase K1 and sacrifice maybe a bit of saying, okay, let's not factor in margin so heavily. We need to get rid of stock. An alternative could be the financial director says, guys, we need margin. We're not worried about stock this quarter or this week. In which case you would up K2 and reduce K1. So with enough data, you could actually put this into a machine learning system, because these three numbers here, remember, these are stored by customer, by product. They're just one number or a set of numbers for the product. And these are company-wide, a vector of company-wide preferences based on stock, returns, whatever it is that the company wants, how the company wants to steer the business for that day or week or month. And tuning this can become quite a little gradient descent problem in machine learning. If you have two versions of it, A and B, so one is 0.2, 0.6, 0.8, and the other one is 1.2 minus 0.7, and you compare the two, see how they did, and with some sort of a loss function or an error function, you can start to tune these parameters if you have enough data and enough time. But that's the essence of machine learning. So it's not as difficult as some people assume it is, because it's got scary names. But yeah, that's how simple it is. I think you've appreciated now how natural it is that these things are to do in a graph database. And I don't know SQL very well, but I really would have struggled to do the same in SQL, especially trying to store those very sparse matrices, and especially if I had a lot of data, I would have been quite lost. Okay, that terminates the presentation portion of the webinar, and I hope you have some questions. Thank you, Aya.
Thank you, Joe. Thank you for your presentation. So yes, we got some questions here. So if you give me just a couple seconds. Okay, so the first question that we have here, Joe, can I use PostgreSQL extensions and functions in AgensGraph?
Yes, you can. So Postgres is really, AgensGraph is a modified Postgres. We took the code, modified the parser in the code so that it would understand that beautiful language Cypher. So that's what we did. So it's still Postgres, and you can still extend it in any way. We have customers using PostGIS. I can't name another extension that's being used, but certainly PostGIS, which I think is the #1. Yeah, so we support extensions. It might be of interest for those people who are sensitive to the difference between a fork and an extension, that we have announced that next year we will have a beta version of an extension of Postgres that implements AgensGraph. So for today it's a fork. In the future it will be an extension. There may be a performance hit. We're not absolutely sure yet, can't confirm. But next year we will have AgensGraph as a fork and possibly an extension.
Thank you, Joe. Okay, the next question that I have here for you, actually it's a really interesting question. Can we write functions in AgensGraph? Does AgensGraph support procedural languages?
For sure. Some of it's to our credit. It exists already, the fact that you can write procedural languages in a host of different languages that are supported by Postgres. There's PL/PG/SQL, which is a procedural language that's just almost native to Postgres. We also have PL/Python, which allows you to write procedural language in Python inside Postgres. And we have the product PL/PG Python as well, which is a third way of, PL/PG Cypher. I haven't used that myself, but I've used the other two. So yeah, there's a variety of different ways. You can also write, by the way, procedural language outside Postgres in Java or Python or your favorite language. And then we have connectors to Postgres. So you can submit your queries via a connector to Postgres and then parse the results as they come back. And you can submit either SQL or Cypher queries.
Thank you. here, does AgensGraph support high availability?
So natively, Postgres supports a variety of different availabilities, but for there's a great project going on called Stolon, which is available on GitHub, and we have connected ourselves to Stolon. So yes, you can have high availability via a third-party Stolon, S-T-O-L-O-N.
Perfect. Thank you, Joe. And I think the last question that we can take for today will be, can I use AgensGraph on cloud environment?
Yes, absolutely. In fact, we have on Amazon Marketplace, we have an implementation of AgensGraph. So if you go on there and choose which server you want built and which product you want on it, you can choose AgensGraph and you start working away immediately. If you're a cloud service provider yourself, you're very welcome to take AgensGraph and make it available to your customers. You do your own charging model, and we'll talk about licensing in that instance for you.
Perfect. Thank you, Joe. Thank you for the answers and presentation again. If it didn't answer any of your questions, we'll get back to you soon. And please let us know if you have any other question. You can always email us, or you can always reach out directly to Joe.
Okay, what I'll do is I'll tell you what, I'll just pop my email address up here. So if anybody wants to email me, you can email me. If I could only type 1 second now. So this is my email address, joe.fagan@bitnine.net. And I'd love to hear from you. Great. Thank you very much.
Thank you, everyone. Thanks again for joining us. And we really appreciate you being here. Hopefully, we see you soon in our next webinar.
Thank you.
Thank you, Joe.